Alright, so this is going to be the tutorial on Dr. Osbay's Project 2 in ANSYS Fluent. So to get started, we are going to drag and drop our Fluent. And the first thing we're going to do, I've accidentally double-clicked into our geometry, but we are going to have to switch this from 2D to 3D, or 3D to 2D, sorry. And then we can go back into geometry. And then we can start modeling our flat plate in the XY plane. I'm actually going to switch this to centimeters. Going to do a rectangle. A very thin flat plate. We can dimension it. This needs to be 100 centimeters. And this can be 10 centimeters. That way we have our flat plate. And then we can go back to here and make our surface. Hit surface from sketches, apply, and generate. And that gives us our surface. I'm going to save this really quick. Save project. Going to click out of here. Go into our mesh by double clicking, and then we can start our meshing process. Alright, this has been opened up. Alright. Now we can, so if we insert a face mesh, this is what will happen. So we hit that, apply, we hit generate. It creates just this. This isn't really good enough for what we want, so we have to do a little bit more tweaking. I'm going to insert a sizing, and I'm going to hit the top and bottom edges, hit apply. We are going to do number of divisions. Number of divisions is going to be 60 all around, pretty much. We're going to use that as a baseline. We have to turn off capture curvature for everything and make our behavior hard. No bias, we don't need that just yet. This should be good. If we hit generate, and then, so now we have more nodes, but we still want it to be more focused at the bottom. So what we're going to do is right click and insert sizing. And we're going to hit our inlet. And then basically do the same sort of process with a little bit of different steps. Number of divisions is going to be 60. Capture curvature, no. And hard. So now, since we want more at the bottom and less at the top, we're going to apply a bias. And then we're going to hit this with a bias factor of 70. And as you can see, this takes the plate and puts more nodes at the bottom and less at the top. And then we can hit generate. And so now we have more nodes. But we need to do the same thing for the other side. That way everything lines up correctly. Apply on our outlet. Number of divisions is going to be set to 60. Capture curvature, no. Behavior, hard. Again, we're going to apply a bias. Bias factor of 70. And we have to reverse it this time because this is at the bottom, rather at the top. Apply. Then we should be good to generate. And there we go. There is our mesh. See, more focused and concentrated towards the flat plate, and less at the top. And so the last thing we need to do is name everything. So inlet, for inlet, I'm hitting N to name my selection. Outlet, this one's going to be the plate, and this one is going to be the free pressure. All right, now we should be good to start setting up our simulation. I'm going to right click this and hit update. And it's going to take its time updating. All right, now we should be good to set this up for the simulation, double precision, 2 solvers, and hit start. And this is loading up. All right. So now everything you can see is set up properly in ANSYS. All right. So we're going to have our material is going to be air. I remember it said it wants the density to be 1.2 and the viscosity to be 1.8. Cell zone conditions, we don't need to worry about that. Boundary conditions, we know our inlet, internal, outlet, wall. This one we can change to just symmetry, I believe. Because it's not going to be a wall. So we can just add it, set it to our symmetry. Everything else we can leave as is. We do actually need to change our inlet though. Our velocity is going to be, I believe it said 2 meters per second. Yes, 2 meters per second. Apply, let's see. Cell registers, monitors, blah, 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 blah. All this should be fine, I believe. And then, just double check. All right, so what we can do is actually hit residuals and make this a little, everything more accurate by adding a few more zeros. Okay, and then I'm also going to double check the plate conditions. No slip, stationary, standard, apply. All right, everything is good. There's also steady, pressure based. Everything here is good. Methods, we're going to do a simple scheme. Everything else should be good. And then monitors, controls, everything here should be good. I don't need that. Initialization, standard initialization. Compute from the inlet. Everything here should be good. We can hit initialize. And that should set it correctly. And then we can hit run calculations. We're going to put 10,000 iterations and then hit calculate and let ANSYS do its thing. This might take a few minutes depending on how strong your computer is. Just going through 10,000 iterations. All right. So everything is done. Now we can look at our plots and contours. We are going to look at all of our pressure contours, our static pressure contour, dynamic pressure, our total pressure, and we can also see our velocity along the whole plate. So let's see, what else were the other requirements that he had? He had get the velocity with vectors. Oh, let's look at the velocity with the vectors. So what we can do is double click on vectors. Velocity, color by velocity, and then I believe we could just hit save and display. And then hit close. And then what we can do is hit scene, contour, save and display. We can make this a bit more transparent. And then that gives us our contour with vectors. And as you can see, there are the velocity profiles. And then we can zoom in even more towards the sort of boundary layer as it starts to develop. And we can close this. That gives us our velocity profile with the contours. Let's see, now we can also start to plot stuff. So we can go to XY plots, and then we can get, what were the, so first we can look at the wall shear stress and skin coefficient. So we can go down to wall fluxes, go down to wall shear stress for the plate, and this will give us our wall shear stress. And then we can have our skin friction coefficient, which is relatively the same. The same sort of plot, different values, obviously. And then what we're going to want to do is, so he wants the velocity profiles at 25 centimeters, 50 centimeters, and 75 meters. And so, sorry, go back to this. And then we can go new surface, line rake. X is going to be 0.25 or 25 meters. So this is in meters. So 0.25. Sorry, 0.25. 0.25 because this doesn't change. And then 0 to 0.10. And then I'll just rename it X20. Sorry, 25. Create. And then we can get the velocity magnitude at here. Okay, so I created more points because I realized he wanted all of the points on the same graph. So go back to here. We don't want this to be positioned on the x-axis. We want this to be I'm trying to figure this out. What does he want? Mesh, sorry. Mesh and y coordinate. Save and plot. And there we go. Okay. That's what I was doing wrong. So in order to see everything, we don't want our stuff to be positioned incorrectly. So we want to basically turn off position on x-axis, set it to the mesh, and set the x-axis to the y coordinate. And that will give us our velocity magnitude. Save and plot. And then to write it to our files, obviously we hit write to file. It'll write it to a text file, and you can use that and export it to Excel. The last thing that he wants us to do is get the drag coefficient. So what we can do is report definitions, new drag force coefficient for the plate. We can hit compute, and that will give us our drag coefficient for the plate, which is 0.028201. So that is how you create and model a flat plate simulation, and along with getting all of the plots for Dr. Osbay's second Fluent project.